In standard calculus, math moves forward. We start with a known function, a clear set of rules, and we process it to find its exact rate of change. We map out exactly how fast a car is accelerating or how quickly a population is growing based on a master equation we already have. But in the real world, nature rarely hands us that master equation first. Most of the time, we only get to observe the output. We can measure the rate at which heat dissipates across a metal plate, or track the speed a virus spreads through a city, but the underlying rules driving those events are not immediately visible. This comparison outlines the core difference. If calculus is finding the derivative, a differential equation is how we work backward. We take that observed derivative, the measurable rate of change, and we use mathematical methods to find the unknown original function. To understand how to break down and solve these complex problems, we can look at the academic framework developed by Dr. Nouro Akmal Mohammed. Her notes serve as an essential manual for decoding these mathematical structures. Mastering differential equations provides a methodology for identifying the functional rules that govern a system's behavior, based solely on its observable output. Looking at this definition from the text, a differential equation is any mathematical statement that contains the derivative of one or more dependent variables, the quantities we are tracking, against one or more independent variables, like time or distance. Mathematicians write these equations in different dialects. This slide shows the classic Leibniz notation. You'll also see shorthand variations. Prime notation uses tick marks. Newton's dot notation places dots over the variable. They all represent the same rates of change. Recognizing these notations is a required first step. Before we can analyze a system, we must be able to accurately identify its components, no matter which mathematical dialect is being used. Dr. Mohammed's notes lay out a strict classification system, starting with type. This slide defines an ordinary differential equation, or ODE. An ODE is characterized by derivatives that involve only a single independent variable. We contrast that with partial differential equations, or PDEs. As you can see here, PDEs map complex systems involving multiple independent variables, meaning the system is changing across several dimensions at once, like a wave moving through space over time. The second classification step is finding the order. The order of an entire equation is dictated simply by the highest derivative present within it. In this example, because we see a second derivative, the whole thing is classified as a second-order equation. Categorizing an equation by its type and order immediately informs our approach, narrowing down exactly which mathematical tools we need to rebuild the original function. Next, we classify by linearity. A linear differential equation follows specific rules. Looking at this standard form, the dependent variable and its derivatives can only ever be to the first degree. No squaring or cubing the y terms is allowed. This slide details the second rule. All coefficients attached to those variables must depend solely on the independent variable, x. They can never be functions of the dependent variable, y. Here we see exactly how those rules are broken. If a coefficient depends on y, as seen in the first example, or if there is a trigonometric function of y, like sine or cosine in the second, the equation is classified as nonlinear. Finally, we check for homogeneity. If a properly arranged linear equation equals 0, it is homogeneous. If it equals a function of x, meaning there is an external influence on the system, it is non-homogeneous. Profiling an equation's linearity and homogeneity acts as a diagnostic test, identifying the specific integration strategy needed to find the original function. So what does a solution actually look like? As this text outlines, a solution isn't a single number. It is a complete mathematical function that, when substituted back in, reduces the original differential equation to an identity, meaning both sides balance perfectly. We can verify this through substitution. If we propose that y equals 1/16 x to the fourth power, we calculate the derivative for the left-hand side, plug the original function into the right-hand side, and confirm they are equal. Solutions come in two forms. This shows an explicit solution, where the target variable is neatly isolated on one side. Below it is an implicit solution, where the dependent and independent variables remain grouped together in the formula. Solving a differential equation is the process of proving that a specific functional relationship flawlessly satisfies the observed rules of change. Because we are working backward from a rate of change, we often have a missing piece of information, typically the starting position. Because of that gap, our math doesn't output one unique answer. It outputs a whole family of possible solutions. This document defines that result as a general solution. It's an equation containing an arbitrary constant, usually written as c, which represents all these possible parallel paths the system could follow. When we observe specific initial conditions, like the exact temperature of a plate at the start of a measurement, we can pin down that constant. By solving for c, we find the particular solution, the single definitive curve we are looking for. Nurul Akmal Mohammed's framework provides the tools to move from observing a system's change to calculating its governing function, allowing for a precise mathematical description of dynamic events.